Good. Now we will talk about different things, and I need to get this thing. I will start. I shared this presentation with Benjamin. I was basically the client in this scenario. I used Ontopic's fantastic product, Ontop virtual graphs, and one of the first data sets I actually produced ever in my life in 2011 was a data cube. And I remember it made totally sense for me to put RDF cubes in an RDF form. And when I showed that to people, everyone was asking me, like, why are you doing this? RDF is for metadata. And I didn't have any clue about RDF. For me, this never made sense. It always made sense to use data in RDF. And as you all know, cubes are tables, CSV files, XML files, whatever you want to call them. And tables can be potentially very, very big. Maybe not in Excel, but when you get CSV files, you can get really big tables. So what is the semantic of a table? That's very simple, right? The semantic of a table is columns, rows, and cells. That's how Excel sees tables. That's how many, many people for a really long time work with tables. But for us, it's obvious that when we use the tables, when we do something with this stuff, that's not the semantic we want to talk about. This doesn't really help us. So there is a ton of implicit semantics in the content of the tables. And it's really, really hard, if you are not the owner of the table, to understand what this semantics is about. And I was thinking about showing another example here. I actually once had to transform Arabic data to RDF. This was the weirdest experience I ever had because I couldn't even read the column headers, right? We are used to the fact that we can read the first line in a CSV or an Excel file and somehow interpret the semantics given by these terms in there. And then we can say column A is probably the ID because it's increasing and it says ID. Then city ID, I do use Wikidata. I know these are Wikidata identifiers. Temp, probably temperature. When I look at the range, probably in degrees Celsius. Timestamp, I work with tables long enough that I know this is a properly formatted ISO timestamp. And we all know every single damn database has their own representation of timestamps. So it's horrible, horrible, horrible. Up to this point, I have to tell people, give me ISO timestamps. I don't care about anything else. So when I then take these things, I can take the red interpretation and say, a row in this table is probably a temperature measurement at the specific time and place. That's the interpretation of one row. So this is great when you are in this domain or when you own your data. You don't have to do a lot of work. When you share this data, you are completely lost. City table, same. I won't go into details. A row represents a city with its name and ID. So here we have joins. Sometimes this is denormalized in one gigantic flat structure, right? So what we now do when we transform this to RDF, we stop guessing the semantics. We want to make them explicit. And this is not something RDF or we invented. OLAP cubes, OLAP tables are very, very common. And in there, the semantics is still relatively general, but we call the columns dimensions, the rows observations. So let's do that. We take one row and we say, an observation is a temperature measurement at a specific time and place. We figured that out. So we have observation 1. We give the dimensions. We can name them. We are in RDF. We can really give labels to these dimensions. And we have literals with data types. So we can really type this information. We can say with some additional metadata that this is degrees Celsius and not Fahrenheit, for example. We can say that this is an XSD date time data type. So we have additional information which we make accessible. And we are in RDF, we do things, not strings. So the join is done via another node which represents the city. And we can attach as much metadata to this additional identifier as we want. That's what we do, right? So when we now create a cube model in RDF, we start to have metadata on several levels. You will most likely want to have a cube metadata part. And that's interesting because when you get the CSV file, you have no idea what this thing is about. If you are lucky, you get a file name which is informative enough that you can figure out what the data set is probably about. So this is stuff you would attach on the cube metadata level. This can be name, date, publisher, description, whatever you want in as many languages as you want to add. The dimensions, we already saw this. We can give a name for the dimension. We can give descriptions. We can attach proper units to it. We can have information about scale, nominal scale, etc. So we can do all these things. And obviously, we can add data types. So it becomes much, much more explicit what we do. And then in the end, we have the observations, or to be more specific here, a set of observations which you pull together and we can do something with it. So that's what we did, or what we do here, and we call this cube, OLAP cube, and OLAP stands for Online Analytical Processing, and it's typically a multi-dimensional array, aka hypercube. Again, I think this stuff was invented by SAS in the 80s or something, or Dave McComb probably knows even better. So it's not a new concept. We do the same thing basically in a graph representation in RDF. There are existing cube vocabularies. We use one which is called CubeLink. You can look up why we did our own. There is in schema.org something called schema.org observation. In general, all these vocabularies have the concept of observation in it. So this is very similar. The way they do the metadata is a bit different. Then there is semantic sensor network ontology. I think this is the one you used in your examples. Or
I used the CubeLink, but
okay, later. Okay, so initially it was semantic sensor network ontology. We have the concept of an observation there as well. And what I call the original, this is what I used in 2011. This is the RDF data cube vocabulary. This basically set the stage. I have some problems with it, which we describe in cube.link. You can see why we didn't use that. But they are all very similar. You could transform one into the other with more or less loss, depending on which model you use. So why would you do that? When you represent your cube in RDF, you can then start to build applications on top of it. And we heard from Aura, we need applications, right? That's what pays the bills. So I can go to an endpoint, let it read cubes, and I can have a cube viewer, which basically looks like an Excel file. So it fetches the data. It gives you a feeling like this is an Excel file. But when you go into the details, you will see this is RDF. So the concepts that are around it are things, not strings. You saw that I switched the language. I can have pivot filters in it, and so on. When I have a standard model, we can build applications which can consume this standard model. This is very, very important if you want to have uptake. The Swiss government actually had something else in mind. Do I need to press play again now? Yes. So this is a platform. This is triple the speed of using it. So just to give you an idea, you can go to an endpoint, it will fetch the cubes, it gives you a preview, and then you can create dynamic visualizations. They use this to embed dynamic graphs into Adobe Experience Manager, for example, for publications, or to create static graphics out of it, or whatever you want to do. You can even share that in a PowerPoint, and PowerPoint with the web plugin will give you a live update. So it analyzes the cube. It benefits from the initial metadata you gave. It's much more tailored than when you would do the same thing in MSBI or in Excel, because it interprets the metadata and gives you things that make sense. If you don't have a time aspect on it, you cannot show it on a timeline, so you cannot choose it. So it guides the person through this process. And one of the users actually sits over there, and she said it very well when someone asked what's the difference to MSBI. And she said, in MSBI, it takes me days to weeks to make a representation, and with Visualize, I can make a cube visualization in 15 minutes. So different use case, different audience, and you can really guide the people because someone provided the metadata. But you have to do work. You have to get the data owner a way to augment, to lift the CSV file. For that, we have a backend application, which I really just tease you to inform you that it's there. People can upload CSVs. They can then create the observation table. They can then create the dimension tables. And they are guided through the process of adding all this metadata. So the front end basically nudges you into adding all this information explicitly, which you only have in your brain as data owner. This is the process of it. This is not necessarily a fun process to do. Most data owners actually don't like doing that, but you have to do that when you want to make things reusable. These two things, the Visualize platform and this cube creator, is open source by the Swiss government. We and another company work on that. Talk to us if you want to know more about that. But now we will see what else we can do when we semantically lifted RDF cubes.
Thanks. Yes, so once you have your data already in a relational database, or you have it in files, so like CSV, JSON, or Parquet files, and you want that data to be made available in RDF. So one way to do that is to use an R2ML mapping. So R2ML is the W3C standards for dealing with SQL systems. And the good news is that even if you have files, nowadays it's pretty easy to use to make them visible as tables and then to query them from tables. So you have systems like Dremio or DocDB that can do that. You have a long list of that. And once you have your mapping, so you can use it in two different ways. So let's say the classical ways is to use it for materializing. So it means you will transform your data in an RDF and load it into a triple store. But you have another option also with the mapping is what we call virtualizations. And basically, when the user makes a query, this query will be translated into a query that will be run over the source. So we generate a SQL query that will run over the database or whatever the database is. So, and well, I mentioned user queries, and so traditionally the user queries used to come in SPARQL. So if you want to do visualization, you can use, for instance, a system like Ontop, or otherwise you can use a triple store. But the thing we would like to show you today is that we also have another solutions for querying the data also in SQL. So the data of the knowledge graph can be made also available for an additional interface. And the solution we have currently is only for virtual knowledge graphs. So basically, with that solutions, we are able to automatically generate what we call virtual tables out of and expose all the data that is in a default graph. So these views are automatically generated. You don't have to do extra effort because we want to have kind of an on-par experience as with SPARQL. So you have your mapping, you may have your ontology, and with that you can automatically materialize or you can automatically virtualize and queries in SPARQL. So we want to have a similar kind of experience with SQL. And basically what we are doing is that we are creating for each class that we are using, so we're creating a table. For each object property, we also have a table, and as well for data property. So you may think that this data then is getting super normalized, but actually to make it nicer for the users, we also denormalize it as much as we can. So it means that if you go to a table about a class, you won't only see the instance of the class, but you will see all the possible relevant columns talking about these instances. So if you have a table about person, you won't get only the ID of the person, but you get the first name, last name, email, address, blah, 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 the company they're working for. So in that way, by denormalizing, then it makes it much easier for people to query because then they don't have to write joins. So the goal here is to minimize the number of joins they have to write themselves. Yeah, and the last point, because we like data to be linked as much as possible. So when we can, we also create what we call foreign keys. That's one way to make links in SQL. So cannot always do it, but when we can, we do it. So to give you an idea, an example based on the cube.link ontology that was mentioned before, I did a small experiment with some data. And for instance, here we go on a constraint. We have a constraint class. So we have a table related to that. And here on the right, you see an example of all the columns you can get for a given row. So not only get the constraint ID, but we get information about measure, dimension, the sensor dimensions, and time dimensions, and some of their attributes. And you can see it's full of URLs, so it's very, you clearly see comes from RDF. But one of the main points for us to get access in SQL that attracted us is to be able to use business intelligence tools out of the box directly. So our solution, basically, we are regularly testing it with Tableau, PowerBI, and also Metabase, and other tools as well. And if you don't, I would like to show you a quick demo based on Metabase, which is a nice tool for exploring the data. So basically, you see that our data is organized in 3 different schemas, one for classes. You see all the classes we have, one for data properties and one for object properties, so that we are sure that in any case we have all the data from the default graph. But in normal use cases, you focus more on the classes table. So here we will have a look, for instance, at the cube table. So if I click on it, I see some of the columns that I can get from it. So I get the cube ID, the name, and links to other objects like the constraints and the observation sets. I can really quickly have an idea of how many cubes I have. So here we're talking about 31,000 cubes. And there it's quite a lot because we used from some open data from our region in Italy, and where we have like 100 different kind of cubes there. So if you want to focus on some cubes, we can apply some filters that are, thanks to foreign keys, they will go to observation constraints, to other tables, and we can, for instance, choose the measurement dimension based on the name. So we have a long list of names, we can select from it, and here, for instance, focus on air temperatures, cubes, time series. So we get a list of not only 243 time series cubes, and let's focus on the one in, for instance, in Anterselvo di Sopra. So it's a place where we have the biathlon stadium where the next Olympic Games we hold. So it's supposed to be a cold place. And then from it, we can go to the observation set and see all the observations that are connected to that observation set. And you see, like here, we have about 400,000 observations. So we can go on the table talking about these observations. Of course, we don't see all of them. We only see the first 2,000 ones. But then we can run aggregation that will run over all this data. So here we take the average air temperature, and we group by per day. So you want to get the average temperature per day. So we run over that. And you see, we get quite a quick answers. And here we are talking about almost 3,000 days. So we can visualize that per day, and if you want, we can also visualize it per month if you want to have a smoother curve. And then we can also have, can decide, okay, per month, per year, so we can see what are the hottest and coldest months over almost 10 years. And not surprisingly, you see that January is the coldest month there. All right, so talking more about performance and scalability. So in that demo, basically, the data you were seeing was loaded in a timescale DB. Timescale DB is an extension of PostgreSQL specialized on time series management. And the machine on which we were running things actually was pretty small, but the data set was relatively large. So we are talking about single logical tables with almost 500 million rows inside. So we use timescale DBs, and these things work very well, especially compared to the experience we had before with a very regular Postgres database that was much bigger but was suffering to deal with this kind of specialized kind of data.
Good, so we were caring about scaling, and I still remembered people who tell me like this will never work, you cannot do SPARQL over data sets like this. So I wanted to do a challenge, and the challenge was that we had the environmental agency in Switzerland which told me like we have potentially up to 1 billion observation from waterways, for example, rivers, whatnot, like temperature, flow, and so on. So this has to go up to 1 billion observations. So let's, and then I said, okay, let's try that. And I figured out DuckDB, which is dubbed as a fast in-process analytical database. Think of it as SQLite for large tables and time series, because you don't have a daemon. You create an index file on the disk, and then the JDBC driver connects to this thing directly, no daemon in between. There is a detailed blog post. Have a look at this for details. I just want to show you basically the numbers. So we have 1 billion rows. I created a synthetic table with the one you saw initially with temperature and city. I took the cities from Wikidata and then randomly assigned temperatures. We used Ontop with lenses. I will not go into details, but you need the lenses to get proper fast SQL queries for DuckDB. And I run this on my MacBook M3, standard machine. It took literally only minutes to load 1 billion observations. It really blew me away, and to create an index. It was so fast, I was like double checking if I loaded the file with 1 billion observations. And then I did 2 SPARQL queries. You will see them, a count just to prove my point, and an average like what we saw just before. So this is the average. I do a cube observation, so I take them, I get the dimensions temperature, time, and city. I group by the city. We also get the label from the city, and I filter for 1 year. And the number you will see on the next slide is from a cold start. So I start on top, I execute the query, and I wait over 1 billion observations. And the cold start query returns in 7 seconds. It did aggregations in 7 seconds over 1 billion rows. Then I run it again. I changed the filter, which you didn't see before. I changed the year, and I run it again. And from that time on, I get aggregations below 3 seconds. So yes, this stuff scales. If you have 100 millions, you don't even wait for the results anymore. With 1 billion, you have like this 3 seconds. So yes, these are solvable problems. We don't have to worry about that stuff anymore. And just to prove my point, it's 1 billion observations. Good, then I materialized the thing, because maybe you want to run that in a triple store. This created mind-blowing 210,000 triples per second in materialization. It took me 5 hours, 15 minutes to materialize 4 billion triples, which was a gigantic 590 gigabyte and triples file. How about RDF triple stores? I shared this blog post, and then Hannah Bass contacted me and said, we can get there in Clever, a new open source triple store. She will have a presentation this afternoon if you want to know more about what she is up to. This problem is not solved yet, but she told me, don't worry, we will solve it. So, to finish, why cubes? It's really beyond CSVs. You want to have clear semantics for everybody else than you as the data owner. That's the point. That's why you do the work. We want to share this information. We can do much, much more if we can relate different data sets without spending 3 days pre-processing that stuff in my local data warehouse. Make implicit knowledge explicit, and as we saw, this also benefits for SQL use cases. I really, really like this idea, and I want to explore that more, because then we have existing tools, people which know how to query large tables. They don't have to think too much. But we benefit from the unification of RDF. I think Dave McComb will talk about that later. So data becomes also more discoverable because you can put it on the web, right? RDF and SPARQL is on the web. So then we can do additional stuff. When Zurich started to publish their cubes, Basel said, hey, we have the same dimension. It's called differently, but we can join this stuff now over the web with federated queries. So you can start doing stuff which is simply not possible when you leave your stuff in CSV files. We could later use OWL for at least same as, right? That's a very useful thing for simple concepts like that. And if it's not exactly same as, you can express semantically why it's not exactly the same thing. So you can add even more metadata to it if you want that. We just have a discussion to extend the model right now to describe in which range a value is, you know, how accurate is the result we have in there. We can describe that semantically. And again, virtual SQL tables will benefit from all this work to do, and data becomes more discoverable. And I think that's it. Talk to us when you want to know more about these solutions. Everything you saw, with the exception of the SQL interface right now, is open source. And there are several of my colleagues here, also Michael Lucken, which, can you quickly raise your hand? Yeah. And Peter, exactly, so they were heavily involved in CubeLink. Talk to them if you want to know more. Thank you very much. Okay, I already used 5 of my minutes, sorry. Questions?
Could we make SPARQL results directly in other cubes? Like?
Yeah, so you mean, could we have SPARQL result sets that we could use as a table then? Or yeah, so Benjamin and I were like brainstorming about these ideas. I think it's a very interesting question. You told me we need to figure out how we can map it to a table in a declarative way, right?
Yeah, to do SQL of SPARQL endpoints, yeah. In many of the ideas of what we implemented could be generalized, so, but clearly that's mostly now some engineering work.
So if you have use cases, talk to Benjamin. I definitely want this.
Thanks so much. Adrian, just a clarification. So the data cube or RDF cube representation is the model, is the meta model, how the observation data is being modeled or moved to mapped to RDF via R2RML mappings.
Yes.
This is correct. So this
Correct.
is the underlying standard. Okay, I'm just wondering, the SQL interface, which was mentioned, which is not part of the open source. How about this? So is this so this is operating yet again on the R2RML mediated view, right? Could you just maybe explain a little bit how it looks like, and would it integrate into the RDF stack, or it's just a separate relational only API? Thank you. So the SQL interface you mentioned, the SQL queries, the raw SQL queries. Thanks so much.
Yes, so the SQL interface is above the RDF knowledge graphs. So, and the RDF knowledge graph is a virtual one. So, so virtual knowledge graph, it means it's defined from the mapping, from the ontology. We can do lightweight reasoning. And obviously, we exploit a lot all the structural information we can get from the database. So, in order to show you additional columns, I have to make sure that I can not get more than one value for each row. So because I really want to have my the ID to be a primary key. Because otherwise, if I run aggregations, if I don't have a primary key, I will get completely wrong results. So, so we do get this information by analyzing the database. And if you get CSV as input, you have 0 constraints almost that comes in. So that's why we have a mechanism called lances to declare yourself constraints holding over your data. So then we can do many optimization, but you can also decide how to represent data, find foreign key relationship, and things like that. So yeah, the more if you wanted to get it well denormalized at above the knowledge graph, you actually need to know a lot about the underlying structure. Otherwise, you will have to end up in a very normalized way of viewing the data, a bit like in SPARQL. So, yeah. So yeah, we exploit all the possible information we can, and yeah, and that's the result somehow.
And technically, what right now happens is SQL to SQL. So basically, the SQL query gets transformed to another SQL query, and the idea what Sherwin mentioned before would be a similar concept, but then we map it to a SPARQL query in the end.
Yeah.
Good. We have to stop here. Thank you very much. Come to us if you have more questions.